Welcome students. Today we will study the chapter of elasticity. You know that when a single force is applied to a body, then the body moves along a straight line or along a curved path, or a single force creates translational motion. But when two equal and opposite forces are applied to a body, which are known as balanced forces, then any dimension or dimensions of the body, that are size, volume or shape, or all three, may change. Such a change is called deformation. The forces which cause deformation of the body are called deforming forces. For example, when a rubber band is stretched from both the sides, its length increases. Increase in the length is called deformation, and the forces which cause this deformation are called deforming forces. Now, what is elasticity of a body? It is the property possessed by a material body by virtue of which the body opposes any change in the dimension within the elastic limit and regain them when the deforming forces are removed. According to this definition, steel is more elastic than rubber because steel has greater ability to oppose the deformation. The elastic body is a body which possesses the property of elasticity, or it is the body which opposes the deformation within the elastic limit and regains the original dimensions after removal of deforming forces. For example, all metals are elastic in nature. The body which do not possess the property of elasticity, or the body which do not oppose the deformation and cannot regain its original dimensions after the removal of deforming forces, is called a plastic body, or a body which can be deformed very easily or with very small deforming force, which doesn't regain the original dimensions when the forces are removed, is called a plastic body. For example, clay, plasticine, etc. Now, why a body is able to regain the original dimensions? It is by virtue of what is called restoring forces. When deforming forces are applied to a material body, some internal forces are developed in the body which try to oppose the changes in the dimensions. These forces are called restoring forces. If the magnitude of deforming forces is greater than the restoring forces, then the deformation takes place. As the restoring forces are directly proportional to the deformation, this increases the magnitude of deforming forces. If it is still less than the deforming forces, the deformation continues. The process continues till the equilibrium is reached, when the restoring forces balance the deforming forces and the deformation stops. Stress is the internal restoring force per unit area. There is no direct method to measure the restoring force because they are generated internally. But at equilibrium, the magnitude of restoring forces become exactly equal to that of the applied forces. So, stress can be defined as applied force per unit area. Depending upon changes in the size, volume or shape, there can be three kinds of stresses. The first one is longitudinal or tensile stress. When the deforming forces cause change in the length, the stress developed is called longitudinal or tensile stress. The figure shows a metal rod clamped at one end to a rigid support and subjected to deforming force mg. If the suspending load has mass m at the free end, mg will be the force acting at the free end. If r is the radius of the rod, then the tensile stress is force upon area, that is mg upon pi r square. The second type of stress is volume stress. When deforming forces cause change in the volume, the stress developed is called volume stress. If volume of a body is changed by changing pressure applied to it by dP, the volume stress is given by applied force upon area, that is change in pressure dP. The third type of stress is shearing stress or shear. When the deforming forces cause change in the shape of the body, the stress developed is called shearing stress or shear. The figure shows a rubber cube A, B, C, D, E, F, G, H. Deforming force F is applied laterally on the surface E, F, G, H. It is balanced by the friction between surface A, B, C, D and the surface on which the cube is kept. The lateral force applied is called shearing force. Due to this force, the cube turns into a parallelepiped. If the cube is considered to be made up of layers, the deformation in any layer depends on its distance from the fixed layer. So, the stress developed remains the same for each layer. If area of the face is A, then the shearing stress is given by shearing stress is equal to applied force upon area, that is F upon A. Stress is measured in Newton per meter square in SI or dyne per centimeter square in CGS. The dimensions of stress are M1, L-1, T raised to minus 2. Similar to stress, there is change in the dimension also. Thus, when the deforming forces are applied to a body, the dimensions of the body also change. The ratio of these changes to the original dimensions is called strain. Thus, strain is defined as change in the original dimension per unit original dimension, or strain is change in original dimension upon original dimension. Like stress, there are three types of strains also. First one is longitudinal or tensile strain. When the deforming forces cause change in the length of the body, the strain in the body is called tensile strain. So, tensile strain is change in the original length upon original length. As shown in the figure, if capital L is the original length and small l is the elongation due to the deforming forces, then the tensile strain is small l upon capital L. Similar to change in length, there is change in volume also. When the deforming forces cause change in the volume of the body, the strain in the body is called volume strain. Thus, volume strain is change in volume upon original volume. The figure shows a balloon of original volume V, which is compressed by applying deforming forces from all the sides. Hence, its volume decreases by dV. So, the volume strain in the balloon is dV upon V. The third type of strain is shearing strain. As shown in the figure, when a tangential force is applied to a body, shape of the body changes. If the body is considered to be made up of layers, then the layer which is at the greater distance from the fixed layer undergoes maximum deformation. So the shearing strain of the body is given by shearing strain is equal to lateral displacement of any layer upon its distance from the fixed layer. Now the lateral displacement of the uppermost layer is EE dash and its distance from the fixed layer is H. So shearing strain is EE dash upon H. It can be seen from the figure that EE dash is the opposite side of angle theta and H is the adjacent side. Hence EE dash upon H is tan theta or shearing strain is tan theta. Usually theta is very small. For small values of theta measured in radian, tan theta is approximately equal to theta. Therefore, shearing strain is approximately equal to theta. As the strain is a ratio of two similar quantities, its value is purely numerical and it doesn't have any unit. Hence, the dimensions are m0, l0, t raised to 0, or it is a dimensionless quantity. Up till now we have studied 3 stresses and 3 strains. Is there any relation between them? The answer is yes. By Hooke's law, we can find the relation between them. The law states, within elastic limit, the ratio of stress to strain is constant for the given material. This constant is the property of the material and it is called modulus of elasticity. Thus, stress upon strain is constant or stress upon strain is modulus of elasticity. Depending upon different stresses and strains, there are 3 elastic moduli or 3 elastic constants. The first one is called Young's modulus, represented by Y. It is the ratio of tensile stress to tensile strain. When a material of length L and radius R is elongated through small l by applying force mg, the tensile stress is mg upon pi r square. The tensile strain is L upon capital L. Hence, Young's modulus Y is given as mgl upon pi r square L. When there is change in the volume, the modulus of elasticity is called bulk modulus. So bulk modulus K is the ratio of volume stress to volume strain. If a balloon of volume V is compressed by changing pressure on it by dP, its volume changes by dV. Therefore, volume stress is dP and volume strain is dV upon V. Hence, K is equal to V dP upon dV. The third modulus is modulus of rigidity N. It is the ratio of shearing stress to shearing strain. If a force F acting on area A of a body moves the layer of the body through angle theta, the shearing stress is F upon A and shearing strain is tan theta. Therefore, modulus of rigidity N is F upon A tan theta. For small angle theta, tan theta is equal to theta. Hence, the shearing stress is F upon A, but the shearing strain is theta, and then the modulus of rigidity is F upon A theta. The strain is a unitless quantity. Hence, modulus of elasticity has the units of stress, that are Newton per meter square in SI or dyne per square centimeter in CGS. The dimensions are also same, that are m1 l-1 t raised to minus 2. Poisson's ratio. The tensile stress is developed in the body, then the body experiences tensile strain also. This is not only changes the length of the body but also changes the other dimension. Thus, lateral strain is also experienced. Experimentally, it is found that the ratio of lateral strain to the tensile strain is constant. This constant is called Poisson's ratio sigma. It is defined as within the elastic limit, the ratio of lateral strain to the tensile strain is constant, which is known as Poisson's ratio. For example, when a material rod of length capital L and diameter d clamped to a rigid support is loaded with a heavy mass suspended to its free end, its length increases by small l. At the same time, its diameter decreases by small d. Hence, the lateral strain developed is small d upon capital D and tensile strain developed is small l upon capital L. As per definition, sigma is lateral strain upon tensile strain. Hence, sigma is d capital L upon capital D small l. As both the strains are unitless, their ratio is also unitless. Hence, Poisson's ratio is a pure number without any unit. With Searle's apparatus, one can study the behavior of wire under a constantly increasing load. On loading, how the extension changes and what happens to the stress and strain can be studied. In the experiment, every time the strain and stress are measured and a graph of stress versus strain is plotted. The scale of the graph is different for different materials, but the nature of the graph is almost similar to the graph shown in the figure. The graph starts from origin O and initially follows straight line path OE. This portion of the graph shows that within the elastic limit, the stress is directly proportional to strain, or the Hooke's law is obeyed. So, point E is called elastic limit. Beyond point E, the graph takes a curve and reaches point Y such that a tangent drawn at Y becomes parallel to the strain axis. This is called the yield point. It is defined as a point on the stress-strain curve such that a tangent drawn to this point is parallel to the strain axis. This indicates that at Y, strain increases without increase in the stress. In this condition, the wire is said to be flowing. The materials showing this property are called ductile substances. At Y, the elastic limit is crossed, but the metal doesn't lose the elasticity completely. Though permanent elongation is caused, the wire can regain its original size and shape when it is unloaded from Y. When it is unloaded from Y, it follows straight line path YS parallel to OE. Thus, OS gives the strain corresponding to this permanent elongation. After Y, the graph follows a curved path and reaches limiting point L. The stress at this point is called limiting stress. At this point, the wire gets contracted at one or 2 points along the length, or the necks are developed in the wire. After L, the graph droops down to B. The portion LB of the graph indicates that during this portion, elongation continues though stress is reduced or the wire is unloaded. At point B, the necks become so narrow that the wire cannot bear the load and it breaks. During the elongation, work is done by the force. That work is given by the formula W is equal to half load into extension, that is half F into L. This work is stored in the wire in form of energy, which is known as strain energy. Hence, strain energy is also half load into extension. Strain energy per unit volume is called energy density ED. If we divide both sides of the equation by volume, we get the formula for strain energy as ED is equal to half stress into strain. By using the equation Y is equal to stress upon strain, we can get two more formulae for energy density, as energy density is equal to half Y into strain square, or energy density is equal to half 1 upon Y into stress square. For CET, it is very important to know what is elastic limit. As the magnitude of the deforming forces increases, the magnitude of the restoring forces also increase. Thus, a stress is developed in the body, but when the deforming forces are too large as compared to the restoring forces, the changes in the interatomic distance becomes irrecoverable. This causes what is called permanent deformation. Hence, the elastic limit is the maximum stress that can be developed in a body without causing permanent deformation. When this limit is crossed, the body gets permanently deformed. Though this explanation is true for crystalline substances, for non-crystalline substances also this is true. Now, the elastic limit is the maximum stress that can be developed. You can write the formula as the elastic limit, or the maximum stress, is equal to maximum force that can be bared upon area. The elastic limit or the breaking stress of a material always remains constant. Hence, as you increase the area of the material or the wire, the breaking strength also increases, but the ratio, that is breaking stress, always remains constant.